Okay, good afternoon, everyone. So let me start with announcements. Quiz 6 is coming, hopefully sometime today. We're finalizing. Just there's only one issue with the quiz, and then we'll release it on Wednesday. We'll sometime close to Wednesday, we'll release quiz 7. So this week, as I mentioned last time, there'll be 2 quizzes. The deadline for lab 4 is next Monday, if I'm not mistaken. If I'm mistaken, just check the website for the deadline. If you haven't gotten started on that, please do so. And after that, there will be just one more lab, which is lab 5, and that would be it. Is there anything else? Yeah, so that's pretty much all the announcements I had. Okay, let's get started with the lectures. We're going to finish address translation, and after that, we're going to talk about caching. So just as a recap, we have talked about different ways of translating address, virtual address to physical address. We talked about base and bound. We talked about page tables. We talked about segmentation. We have talked about segmented pages. Segmented multi-paged x86 model. Yeah, I guess we've covered pretty much most of the main ways. And now there is one more remaining way of translation, which comes next. Now, before getting to that one, I wanted to talk about shared libraries and address spaces. So if you remember, let me get rid of my, let's just give you the video of lectures. Okay, so shared libraries, if you remember, we didn't want to have multiple copies of them. So we want one copy of the shared library code to reside in physical memory, and then we want everyone to share that code. Now, there is there are some details that we have to pay attention to when we want to do that. I'm sorry. Okay. So when you're sharing libraries, in the code of the library, you might have some variables, global or static variables. Can you share those variables between different processes? The answer is no, because each process that runs the code, it needs its own version of those variables. So we're not going to share the variables. So that's first, put it aside. So we're not going to share those. So each process is going to have their own copy of those variables, and then they're going to have read and write permission on those variables. Now, what about the code? We're going to share the code, right? That was the whole purpose of it. Now, we can actually make processes share the code. We can give read and execute permission to each process. Now, what could be an issue when multiple processes share the same code? Now, if you remember, every time you want to fetch an instruction, you need to have a PC that is pointing to that instruction. So inside your PC register, you're going to have the virtual address of the instruction that is going to be executed. Now, when you compile a shared library, you don't really know to which area of each process your code, your virtual library code, is going to be assigned. So again, I'm taking a step back. If you remember, we said with dynamic linking, you wait until the last moment when the program starts using the shared library routines to link the library into the virtual address space of that program. So up to that point, we really don't know the virtual address of the shared library in the context of our program. Add to that, the same shared library could be mapped to different regions of different programs, different regions of virtual addresses of each program. So why is that important? Well, what should really be the PC, and how should the PC be set to the same code that is going to have different virtual addresses in different processes? To get around this problem, we're going to compile the shared library code in a different way than we usually compile our code. So the code should be compiled to be position independent. What that means is every reference in the code. So remember, we have two different references. We have data references and we have code references. So with PC, that's code reference or instruction reference. So if you're just going through your code, PC is going to get +4 +4 +4. So that's relative. So you set a PC and then you just add to it. But if you have a jump, let's say you want to jump to the beginning of a routine, so that you might want to have an actual virtual address to jump to. Now that jump, it has to be relative. You cannot use absolute addresses. Why? Because there are no absolute addresses. This code is going to be mapped to different virtual addresses, different virtual address regions in each process. Therefore, we can't use absolute addresses. All the addresses in our code, data references and instruction references, have to be position independent. They have to be relative addresses. So how do we do that? The way it's done is by putting a global offset table in our shared libraries. So this is going to be a table with a fixed position relative to the code. Let's say we always put it at the beginning of the code. So the address is known and it's relative to any instruction. So this is actually for data references. For instruction references, it's the same. We'll talk about it. But for data references, remember, data references, any data will be here. You have it. Each process is going to have their own data. So each process has their own addresses for the data and for the instructions. Now, we put this table every time we want to reference from our code to any data. We just, because we know the relative address of this table, and we know each entry corresponds to a particular variable, so we can actually calculate relative address to that entry. So all the addresses are relative to the entries of this table, and once the process is once the shared library is mapped to the virtual address by dynamic by the dynamic linker, the dynamic linker will fill this table for us, because at that point I know the virtual address of all the variables, so I can fill the entries on this table, and then from the code I have relative address to these entries, and then I can just, this is a level of indirection, I can find the real virtual address of each data reference. So the same is true with instruction references. There is another table that is called procedure-linkage table. The same exact concept. Two things here. These two tables, again, are going to, each process is going to have their own version because each process is going to get their own virtual address. So like the global and static variables, we're going to have, each process is going to have their own copies of these tables. Okay, so let's finish our discussion on multi-level address translation. So these are the positive things. We have, so we're not wasting space on the page table. We just allocate as needed. Memory allocation is easy because we don't have external fragmentation. Everything is paged, so the fixed size that we have applies to virtual and physical address, and we can just have a bitmap to know which pages are empty, which pages are allocated, and all of that. So it's easy to allocate. Sharing is also easy. We can just share the same virtual address, virtual pages to the same physical pages. Now, what is bad about it, or what are the downsides? The first one, which is the most important one, sorry, not the most important one. The first one is that if a process uses its entire virtual address space, then we are actually holding or keeping more page tables because we're adding levels, right? If you end up using all the entries, the last level page tables would be equal to the page table that we started with if we were to have just single page table for every virtual page. So that would become your last level pages. But then now you have the first level and second level and third level page tables as well. So you added that overhead. So basically we're keeping extra pointers that might come and bite us if we end up using the entire virtual address space. The second thing is that page tables themselves usually need to be contiguous. You don't want to you want your entire page table to fit in one page. That's easier when it comes to paging, which we will talk about later on. So you want to bring in an entire page that would have the page table inside it. You don't want to have the same page table split between two pages. And the last one, which is the important one, is that for each reference, we're going to use we're going to do multiple memory accesses to get our translation. Like for instance, in x86, for 64-bit systems, you have 4 levels of indirection, and each one of them will require you to go to memory. So 5 references for one. Okay, so now this is the last method of address translation. It's called inverted page table. So what's the idea? So the idea is that in all the previous ones that we talked about, we usually have more page table entries than we have physical pages. Usually physical memory, usually, not always, physical memory is smaller than virtual memory. So is there any need to keep all those page table entries? All I need to know is how each physical page is allocated, right? So to deal with this, you can actually create something like a hash table. The size of the hash table could be equal to the number of physical pages that you have allocated. Let's say if you have allocated the entire physical memory, the size of the hash table will be the size of your physical memory. But if, let's say, you've used only half of your physical memory, then the size of the hash table is half of your physical memory. So you have as many entries as physical pages, and you're going to just hash the virtual page to see where it's matched. to physical memory. So you use the virtual page number as a key, you hash it, you find physical page number, and then you use the offset. And this is actually being used in some systems like PowerPC, Ultra Spark, and such. So it's a very attractive option for 64-bit address spaces in particular. Because in those systems, you have a humongous amount of virtual pages. We saw if you were to just have as many page table entries as virtual pages, you would just to hold your page table entries, you need a lot of memory, physical memory, which is not practical. So in those cases, it makes a lot of sense to just have as many entries as you have in your physical page. Okay, what is the downside of this? Well, the downside is the complexity of managing this hash chain, because you might have two same keys being hashed to the same page table. And if you want to implement this in hardware, then your hardware has to deal with these chains. It has to keep a list of all the hash tables, all the keys that are mapped to the same page, and then it has to handle those. The other thing that this has is that it will give you poor cache locality for your page tables. As you can see there, I mean, we will talk about cache in the next lecture, but it's very hard to reason about where your each address is going to be mapped to the cache by just looking at your virtual address, because your virtual address is going to just be hashed. So we can't have a pattern inside your virtual address to tell us where it would be matched. Okay, so this is an example of that. So I got a question. Doesn't this fail if you have programs trying to use more memory than available? Not really, right? So at the end of the day, all you have is your physical memory. So what would happen if you have programs that are using more memory than available? The same, whatever will happen is the same as what would happen in, let's say, in page tables or segmentation. You have to evict some virtual pages from your physical memory, put them in the disk, and bring some other physical pages, because you have a limited amount of memory. We'll actually have an entire lecture coming about paging, which is basically the same topic of, okay, we have a limited physical memory and the virtual memory is huge. What happens if processes use more than what we have? So with that regard, there is no difference. Any address translation that you use, you might end up with that problem, that you have to evict some pages to make a space for others. But with the hash table, as you can see, with this inverted page table model, the size of my inverted page table is as many as I have allocated so far. So if I end up using all my physical pages, the size of my inverted page table will be the same as the size of my physical memory, which is still good, because the size of physical memory is usually less than the size of virtual memory. So we have a cap on how big the table becomes. The biggest that it could become is as big as your physical memory, the number of physical pages. So how does it work? Well, for each address, you hash it. So you use a hash function, you give it your virtual address, it gives you your physical address. So in this particular example, there is no chaining. So there are not, each one of these virtual pages are hashed to a different physical page. But you could imagine if you have chains, then only one is valid, right? It means that two different virtual pages in two different processes are mapped to the same physical memory. Well, one of them is valid, one of them is invalid, or the rest of them are invalid, because one of them only exists on physical memory, and the rest of them are paged in the disk. So you have to bring them back if you want them. I got a question. So could you explain how we could have two same keys in the hash table if each virtual page has only one entry? No, that's not what I said. I said each physical page has one entry, not each virtual page. So again, the size of this, so the number of keys in inverted page table is as many as we have physical pages, whereas we might have a lot of virtual pages. So virtual page is my key, but the size, the number of entries here is as much as we have allocated in physical memory. So in this case, you have more keys than entries. So it might be that two keys will match to the same entry. And again, in that case, I only have one of those virtual pages in physical memory because my physical page can only contain one page. The other one is probably in the disk somewhere. I have to go and grab it, which we will talk about when we talk about paging. So again, it's very attractive. It's an attractive option, especially going to the 64-bit systems and beyond. Now they're talking about 128 bits systems. So in those cases, this is very attractive because it's almost impossible to translation of 128 bits with the paging and stuff, because it would require a gazillion number of times of going to the memory to just translate one. Okay. So once again, total size of page table is number of pages used by the program in physical memory. So there is a cap on how big the inverted table can get. What we're doing is we get the virtual page number, we hash it to get the physical page number. And if we have more virtual pages than physical pages, then multiple virtual pages might end up being mapped to the same physical page, in which case the hardware or the software has to deal with which one is valid and which one is invalid. Now, lastly, let's talk about address translation hardware versus software. Now, this actually, we had a quiz question very related to this. At least the point is that you usually, almost anything that you can do in hardware, almost anything, can be also done in software. So although hardware does stuff usually faster, you still can do it in software. Let's see how. So the one that we have, I mean, at this point, I've talked about concept of page tables. It's usually in most of the systems that you use, it's implemented inside the hardware. So all you need to have is a unit in your hardware called Memory Management Unit, MMU. So this MMU takes care of all the address translations. All it needs to know is the address of your first level page table. So if you give the unit the address of the first level page table, it traverses that table by itself. So without any need to come to software, as long as the page table entries are valid. So anytime the hardware processor generates a virtual address that needs to be translated, MMU takes care of it. it just accesses the page table level 1, and it traverses your page table tree to find the translation by itself without any involvement of software, as long as those page table entries are valid. If at any point in its traverse it finds a page table entry that is invalid, at that point MMU generates a page fault, basically an exception, and then operating system wakes up to deal with that page table, invalid page table entry. So an invalid page table entry could be for any particular reason that we have seen. It might be that it's actually not allocated, so it's a big fault. You have to terminate your program. It could be that it's invalid because you want to allocate less at the beginning. You want lazy allocation, but then when page table fault happens, then you allocate it. Operating system allocates it, so the page get masked from the program doesn't see it, or any other reason. So at this point, if there is an invalid page table entry, then the operating system will take care of it. So, or maybe if it is, the program wants to write to a page where the page table entry says, no, the program only has read-only write on this page, then page fault happens, and the operating system wakes up to deal with it, right? Another example is, let's say the memory is full, so we have to evict a page. So what we do is that we make that page table entry invalid and copy the data back to the disk. Now, next time our process needs that data, now the page table entry is invalid, so a page fault happens, operating system wakes up, evicts another page, brings back the previously evicted page, and potentially give it another address, so updates the page table entry, make it valid, and then goes back to execute the code. So this is relatively fast because the traverse is being done by hardware. It's a little bit inflexible and complex. Whatever now you fix that your hardware is going to do, it's done. So there, you can't change your method later on. And the operating system might have to, modify its own data structures to fit with what the hardware is doing. Alternatively, you can implement page tables in software. So what does that mean? Well, every time an address is generated, every time the processor wants to access memory, it raises an exception every time. And then the operating system searches its data structures to find the translation, whatever data structure the operating system uses. It doesn't need to use any of the things that we've talked about. Could just use a linklet or whatever. Inside the software, you just need to have that mapping, translate, and then you resolve the fault. So nothing is done in hardware. As you might imagine, this is a lot slower than the first one, because for every instruction, basically, you're going to come to kernel to translate that instruction, which is very costly, but it's possible. So something that we will talk about next is caching. So no matter what you do in hardware or in software, we definitely need to cache the addresses if we really want to accelerate this process. Give me a second. Okay. This is a summary of all the things that we've seen: segmentation, page table translation, multi-level translation, and inverted tables. What are the advantages? What are the disadvantages? I'm gonna go through, so it's just for your reference. Okay. actually one. Okay. So next, we're going to talk about caching, which is where I just ended the previous lecture saying that in order to improve the performance of address translation, we need to cache them. So far in the course, I've talked about caches in multiple occasions. More specifically, I think the most significant one was when we talked about cache coherence. Now let's dive into the issue of caches and see what we can see. So in particular, in this lecture, we're going to talk about the principle of locality, temporal, and spatial. We're going to talk about cache organizations in modern architectures. We're going to talk about major categories of cache misses, and then we're going to talk about the application of caches in address translation. Okay, so let's talk about the concept of caching. So cache, what is it? It's basically a repository of all the things that that could be accelerated, that we access so much, so we can actually have a repository of them to accelerate accessing them. So if you're frequently checking a website and the content of that website is not changing, maybe it's a good idea to make a copy of that website, keep it in your local browser's memory, instead of every time going to that web server to request that web page. If that web page is not changing, so you can just cache it. Instead of going through the network, you can just bring it from your local memory, right? That's the concept of caching. Now, there are a lot of techniques that go to making caching possible. And cache is actually one of the major techniques as of itself that has been used in computer architecture and also computer systems to make systems faster. So we're going to talk about both of them. So what goes into making caches fast and effective, and also how can caching be used to make our systems faster. So caches are only good, I emphasize, only good if you have frequent accesses. If you don't have frequent accesses, they still might be good. If you have infrequent cases that are very expensive, you might want to cache those as well. But if you have infrequent cases that are not expensive, yeah, so if you have, sorry, so I take it back. So if you have frequent cases, then caching is good. And also you should have infrequent cases where they're expensive, because if you have infrequent cases that are very expensive, you might actually want to cache those instead of caching the frequent ones. We'll see that. Okay, so why caching is a trend in performance of our CPUs according to Moore's law all the way to 2000s. And this is the improvement we got in terms of performance of our DRAMs. So you can see there are orders of magnitude difference between how fast a CPU is and how fast our DRAM technology is. The thing about it is that our CPU clocks are so fast that that if your instructions need to go to memory, you will have a really huge gap here. So back then in 1980s, if you needed memory, you would have to wait, let's say 2-3 cycles, whatever. The difference wasn't that much to get your data. But now the cycles are so fast in CPU that you might actually have to wait for hundreds or thousands of cycles for each time that you access your memory. So it's very, very expensive in terms of cycles now. And this performance gap has been growing ever since. Now, why does caching help? Usually, if you look at the probability, so if in this figure on the x-axis, I have the address space from 0 to 2 to n-1. Let's say if you have n bits to address, then you have 2 to n-1. Sorry, 2 to n entities to address. And let's say on the y-axis, I have the probability of each reference. How many times or what's the frequency of a particular entity being accessed? If you profile your application and draw this figure or this diagram, you usually get something along these lines. So there are certain addresses in your addresses space that are accessed a lot. So the probability of referencing those is high, meaning that they are frequently being accessed. And you probably will get a bunch of these spikes in your graph. So this means that there are certain addresses or entities in your addresses space that you frequently are accessing. So it might be a good idea to cache them, to keep a copy of them. Now, there are two different types of locality. There's one that we call temporal locality. That means that if I've accessed a data now, it's likely that I will access the same entity in a short period of time from now. And then you have a spatial locality. It means that if I access location X, then there is a high probability that I will access location x+1 and x-1, and a high probability that I access x+2 or x-2. So any location close enough to the location that I just accessed, there's a high probability that I might access them. Let's say you're going through an array of characters or ints or whatever you have, or a linked list. If they all are assigned a contiguous virtual address, if you access the first entity, there is a high chance that you're going to access the second entity. Or if you, you're running your code, if your PC is now somewhere, there's a high chance that next time you're going to access PC+4, next one. There is a low chance that you're going to jump to a new address, right? So that would be spatial locality. So let's talk about a few terms. Let's define them. So we're going to talk about blocks. This would be a contiguous region that are aligned in bytes, usually like 32 bits, 64 bits, or 128 bits. We're going to call that a block. So we're not going to talk, sorry, byte. We're not going to talk about 1 byte. I mean, theoretically, it's fine to have a block with size 1 byte. But usually in systems, you have a block that is, more than 1 byte. So we have heat rate and heat time. So heating in cache means that you wanted to access an entity. You first checked your cache and you actually found that entity stored in your cache. So that's the heat. And then heat time means how long did it take to realize that you have that entity in your cache. And then a miss means that you actually first accessed your cache and you couldn't find that entity inside your cache, so you missed there. And now you have to go and bring that entity to make it a little bit clear. When we talk about miss time, we mean how long it takes to take care of that miss. So it means that, okay, we have already figured out that the data is not in the cache. Now I have to spend some time to bring that data that I need to access. So the time that it takes to satisfy that request for that entity, we call it miss time. Usually misses are expensive. So if you miss in your cache, it means that you have to go to your memory. If you miss in your, your browser's cache, it means that you have to go to that web server throughout the internet to bring that data. So usually if you miss the cache, if you can't find your data in your cache, you have to pay a high price to resolve that. Okay. Usually, at least when we are talking about processors, our loads and stores are in bytes, right? You say save this byte, load this byte. Whereas blocks, as we said, are groups and sets of bytes. So what happens is that when you access a byte, you usually first figure out which block it belongs to, and then you cache the entire block, or you want to access the entire block. Very related to spatial locality. So every other location that is close to this byte will also come with it. We also have heat rate. This is basically the ratio of the number of hits you get divided by all your references. So all your references either hit or miss. So the number of them is the number of hits plus the number of misses, and then the hit rate is number of hits divided by that, by the total number of accesses you have. And then miss rate is basically 1 minus hit rate. Then you have average access time, which would be, with this hit rate is basically the probability that you hit. And if you hit in the cache, you're going to just, the cost would be the hit time to access your data. If you miss in the cache, if you cannot find your data in the cache, you've already spent the hit time because you already have searched your cache. You now also have to spend some time to resolve that miss. So hit time plus miss time. So if you just, factor hit time here, both of them have it, then it would be miss rate plus hit rate, which is 1. So on all your accesses, you're paying the hit time. So this means that no matter what, you're coming to the cache. So you're going to spend that much time anyways. You hit or you miss. But if you miss, you're going to miss with probability miss rate. And then you're going to spend extra time to resolve that miss. Now, if you look at this, we always want this average access time to be as low as possible. So one way to deal with it is to reduce this miss rate. So basically increase your hit rate. One way to do that is to have a bigger cache. But if you have a bigger cache, so if you have a bigger cache, then you can store more data in it, so you will have a better hit rate. But what happens is that usually with bigger cache comes slower caches. So if you make the size of your cache big, then your hit time will go up because your cache would be slower. So there is always a trade-off. So if you want to now improve your hit rate, this means that you want smaller caches. And if you have a smaller caches, then you will get a higher miss rate. There are other factors, obviously, we'll talk about them. But just to analyze this formula, it's nice to pay attention to this. What do we have usually in our systems? This is usually what happens in our systems. We have, so if you have a multi-core processor, for instance, core 1 and core 2, each one of them will have their own registers. Each one of them will have their own L1 and L2 caches. Then you have an L3 cache that is shared between all cores. Then you go to memory, then you go to the secondary storage, and probably you'll go to another secondary storage. If you look at the speed in nanoseconds, the registers are the fastest. As we said, the smaller they are, the closest they are to the processor, the faster they are. And as you get to the bottom of this list, you get really slow storage mediums. Now, in terms of size, it's a reverse trend. The closest they are to the core, the fastest they are, the smaller they are. So usually you get terabytes of data in your secondary storage. This has changed, actually. I should actually change this. Nowadays, SSDs are also, you can find them in terabytes, not gigabytes. Okay. So this is probably hundreds of terabytes, and then this is like few terabytes. Your memory is still in gigabytes, although right now I'm actually buying a server for my group. It's like we have a terabyte of memory. So that's also not, something very odd these days. Now, in terms of who controls each one of these, registers are usually controlled by the compiler. When you code, you don't, unless you're doing assembly, you usually leave the registers to your compiler. You have your variables and functions and stuff. The compiler manages the registers for you. All your caches are managed by hardware. They're transparent. So when you write a code, you actually don't know how much caches you have, or if not you have any caches. So you might actually don't have any caches. You don't really care when you're writing a program, usually. Although there are cases where you actually optimize your code based on the amount of cache that is available to you. Let's say, I've actually seen this in many research areas. People want to have the fastest code possible. So let's say if you're doing matrix multiplication, it's important how you split your matrices in blocks, and the code usually runs some test to figure out the size of the cache to make sure that the blocks fit in the cache. Because if they fit in the cache, then you get higher performance. So you could figure out the size of your cache. There are ways to do it. We actually talk about it today, or in this lecture, maybe tomorrow, next time. But we'll talk about ways that caches introduce some vulnerability, because in essence, they have to be transparent to the programmer. Programmers shouldn't know that they exist, but because they make it faster and programs can measure how fast their code runs, they're basically leaking information about themselves, and information that should be hidden from users. It should be transparent. And by leaking that information, you're basically creating vulnerability, security vulnerability, which we'll talk about two major, or at least one major one today, in this lecture. And then your memory, your disks, usually managed by software and operating system. So let's say you create a file, you know where in memory you have your data, so the app would be, managed by the software, by your code, or by the operating system. The goal here with this hierarchy is to bring the average memory access time as close as possible to the speed of L1 caches. So we're going to use all these storage mediums to bring the access time as close as possible to L1. It's not entirely possible to have access time equals L1 unless the data you need, all the data your program needs, can fit in L1. But if it's bigger than L1, then the way that we manage caches, we can bring the average memory access time close to L1. We'll see how it happens. So to do that, let's look at the formula for average access time and see if we can now extend it to multiple levels of caches. We just saw it for one. If you have only one level of cache, it would be heat time plus miss rate times miss time. Now, if you have a hierarchy of caches like this, so if your CPU is connected to M1 and then M2 and M3 and M4, these are different levels of caches, then the miss time at level X. So if you miss in M1, what is the miss time? The miss time in M1 is basically the average access time in M2. So this is the rule of thumb. Miss time at level X equals average access time at level X plus 1, which makes sense. So if you miss in M1, you have to go and grab it in M2. Now, what is the time that it takes to grab data from M2? That would be the average access time of M2. Now, given that rule of thumb, let's see if we can come up with a formula. So the average memory access time that CPU sees is basically the average time of M1 using this rule, right? So average memory access equals average time of M1. Now, what is average time of M1? It's the heat time of M1 plus miss ratio of M1 times miss time of M1. Now, again, we're going to use the same concept for miss time of M1. So what is the miss time of M1? It's the average time of M2. And what is the average time of M2? It's basically heat time of M2 plus miss ratio of M2 times miss time of M2, and so on and so forth. Now you can substitute miss time of M2 with average time of M3, and you can keep going, right? Okay. Now, there are caching questions that we have to answer. Okay. So here is an example to set the conversation about what are the concepts that we have to pay attention to, what are the concerns if we want to implement caches. So let's say we have a memory, we have a physical memory that is addressable by 32 bits, sorry, by 5 bits. So basically it has 32 bytes. And let's say our cache is much smaller. It's only 8 bytes. So now we can address 8 bytes with 3 bits. We need 5 bits to address memory. And let's say at this point, each block is 1 byte. So each block in our cache is just 1 byte. Also, so the block size in your cache usually should match the block size in your memory. So if you're you want to say that my block size in cache is 1 byte, you have to look at your memory in that sense as well. Now, assume that your CPU accesses address 01100. Now, questions. Where should I look in my cache to see if I have that entity cached? Which entity in my cache should I search to figure out if I have it in my cache? The second question is, okay, let's say I didn't have it. Somehow I figured out it wasn't in my cache. Now I want to bring it in my cache. Let's say I'm frequently accessing this address. I want to cache it. Where should I put it? It's very close to the first question. So where should I put this? And lastly, let's say my cache gets full and I need to bring in a new entity. So I need to evict one. Which one should I evict? So these are three main questions that we're going to actually answer now. So let's start with where to put blocks in cache. Usually how we address this question is by dividing our caches into sets, and then making a rule that maps each block to one set. Now, each set can have m number of blocks. So if you have m way set associative cache, it means that each set has m blocks. Now, if you have 4 blocks per set in your cache, then you have 4-way set associative cache. You might have fully associative cache. What does that mean? It means that your entire cache has only one set, and that one set basically has all the blocks in it. If you have a fully associative cache, it's very flexible because now every block could go anywhere in your cache. Remember, we're going to map each block to each set. If you have only one set, this means that that block, any block, could go anywhere in your cache because there's only one set. But as we will see, this would mean that access latency is higher. You could go to the other side of the extreme. You can have sets with only one block. So that would be one-way set associative. So each set only has one block. We basically, this has its own name. We call it direct map cache. And that basically means that every byte, every block in memory can only go in one particular location, one particular block in the cache. So there is a one-to-one mapping from each block in your memory to one block in your cache. So basically, there is no flexibility. It's the least flexible, but then it will give you the shortest access latency. Which, as you can see, I have a. This should actually be minus. Because it's not flexible, but it's very fast. Okay. Okay. Now, let's have an example going back to the example we started with. Let's say that our cache is a direct mapped cache. So basically what that means is that, excuse me, every cache, every physical memory is mapped to a single cache location. So how do we do that? Well, we have only 8 caches, 8 cache blocks, whereas we have 32 memory locations. So what we can do is to just look at the 3 lowest address bits and just use those 3 to find the cache location, because we only need 3 bits to address our cache. So if I only consider the 3 bits of my addresses, I can find a valid address in my cache, and I would create that mapping, one-to-one mapping from each memory location to each cache location. So if we go with that, then all of these 4 locations have 100 as their last 3 bits. So they all would be mapped to this 1000. So all of them would be mapped to this one. Now, how do I know which one is cached? Because all 4 of them could be cached. So I need to actually store more data to investigate whether or not I have the one that I really need. So what do? We add a tag to each one. And what is this tag? We'll just keep the last 2 bits as tag, because then these 2 last bits are different for these 4. So this one has 1, 1, this one has 1, 0, this one has 0, 1, and this one has 0, 0. So I cache the value in this location, but I tag it with the remaining of my address. That way, I can basically check. So if I need to see if I have this 01100 cached, I look at the 100 location, and then I compare the tag with my address. And if I get a match, this means that this location now has the value that I need. Now let's do the same thing with fully associative cache. What does that mean? Fully associative cache means that each location, each one of these guys could go anywhere in my cache. So this means that any one of these could go anywhere in my cache because I only have one set. So how do I know where to find it? Well, I need to use more tag. And you might have guessed, I need to actually use the entire address as a tag, because now my memory location could be anywhere here. So all I need to do is to just check my address with the tag. And if I find my tag, if I find my address in the tag, this means that this location now contains the value I need. Okay, so here is an example, putting all 3 methods: direct map, set associative, and fully associative. Now, very similar to the case that we saw. So with direct map, let's say if I have 32 blocks, then with direct map, each location is mapped to a single location. Now, if I have 32 entries in my memory, and I only have and I only have 8 entries in my cache, all I need to do is to just do to get my address. Now let's say address 12, get its mode by 8. So 12 mode 8, that would be 4. So I can find it here. I got a question. So is the type of cache fully versus set associative picked based on temporal or spatial locality? Usually, it's set by the hardware. So the hardware sets your cache's set associativity, and then it would the locality that you have and the size of the data that is local in your workload will behave differently given the set associativity of your cache. Now we can talk about what is the best option if you have this certain type of locality and this certain type of cache size, but in reality it's usually fixed. So when you buy a processor, the type of cache is fixed. Now you should study how your program will react, because you can potentially change your program's behavior, but you cannot usually change your processor's behavior because it's fixed. Now, going forward, so what if I have a two-way set associative cache? With a two-way, if I have 8 cache blocks, so each 2 blocks will belong to one set. So how many sets I'm going to be having? I'm going to be having 4 sets. So in order for me to find my address, I'm going to divide my cache into 2 sets. Each set now has 4 entries. So I just do 12 mod 4. So 12 is basically the address of the entry that I want. So I take the mode by 4 instead of taking the mode by 8, which was used in direct map. Now each set has 4, so I do mode by 4. And in fully associative cache, the location could be anywhere in my cache, right? Now if I look at the addresses, which ones I'm going to use for tag, for direct map cache, I'm going to use the least amount of tag data, only 2 in this case. If I have a two-way set associative, I'm going to use 3 bits. And if I have a fully associative, I'm going to use all the bits, as we saw. Okay. Now let's look at the implementation. How much time do I have? Okay. Now let's look at the implementation. So here I have my memory address. Some of it I'm going to use as a cache tag, as we saw, and the rest of it is going to be used for 2 separate issues. One is going to be used for cache index, and one is going to be used for byte select. Now, why do I have this byte select here and I didn't have it previously? Previously, I didn't need this byte select because each block was 1 byte. But if you have blocks with more bytes, then you need to see which byte of that block you need for your access. So this byte select would depend on how big your block is, and the cache tag is dictated by your set associativity and the size of your cache, and anything that is remaining will be used for cache index. Let's see how. Yeah, so byte select will be used to say which byte we want. Cache index, we're going to use it to see which block in each set we need. And the cache tag is used to find our data, as we talked about it before. So let's see how we implement direct map cache. So let's say we have n bits. With n bits, we can address 2 to n bytes. Now, so yeah, let's say, let's say my cache has 2 to n bytes. So that's the capacity of my cache. And let's say each block is 2 to m bytes. I'm going to make everything to be power of 2. That makes everything easier because we're working with bits. So let's say the cache capacity is 2 to n, and the size of a block is 2 to m. What information we get out of this? Well, the first information we get is that we're going to use m bits. Oh, and by the way, we're talking about direct map cache, right? And let's assume that the base address is 32 bits. So you can extend this to 64 bits. So when you have direct map cache, it means that each memory location is mapped to a particular cache location. So you're going to just use the n bits of your address, the first n bits of your address, to find the location of your memory, that address inside your cache. So the rest of it is going to be used as a tag. So 32 minus n will be used as cache tag. M bits are going to be used as byte select because each byte is 2 to m bytes. So we need m bits to figure out which byte we need. And the rest of it, which is 32 minus n minus m, is going to be used as your cache index. Now let's look at an example. Let's say you have a 1 kilobyte direct map cache with 32 byte blocks. So using the formula above, so you're going to have 32, which means 5 bits for byte select, 32 minus the size of your cache, the log of the size of your cache, which is 10. So 32 minus 10, that's 22 bits for cache tag. And the rest of it is going to be used for cache index, so 5 bits. Now here is that example. So the first 5 bits are going to be used for byte select. The next 5 bits are going to be used for cache index, and the rest of it is going to be cache tag. So again, this is direct map cache. So each memory should be cached in a particular location. So there is only one set. So we only have one set in our cache. And that one set has all the bits, sorry, all the blocks in it. Now, okay, so this is basically all my cache, sort of, right? Each block has 32 bytes. So 32 bytes, these are the data that I have. And then I will have 32 of them, 32 blocks. So 32 blocks, each block 32 byte. That would be 1 kilobyte of cache. So for each one of them, I'm going to use a cache tag. So the cache tag will come from my address. Now I will use the, so let's look at this example. Let's say the byte select is 0. Let's say the cache index is 1. And let's say the cache tag is 50. So the first thing I do, I'll use the cache index to index into my table. Next, I need, so let's say, when do I know that this is a hit? So I have to check the cache tag with my tag that comes from my address. And I need to basically get the byte I need. So these are the bytes. I should have 32 bytes in each block. So I use my byte select, which is 000. So I have to look at the first one. And now I check, see if the tag I have in my address matches the tag I have stored in my cache. And if so, then I have it. Sorry. So, okay, that's all I need to do, right? Now, let's do the same example with set associative cache. So with set associative cache, let's say I have 2 to k way set associative, and let's still say the capacity is 2 to n, and the size of each block is 2 to m, so I haven't changed those. So I still need m bits for byte select. Now, how many bits do I need for tag? To calculate how many bits I need for each tag, I first need to see how many sets I have, right? So I'm not going to do the calculation. So basically, the lower m bits, I'm going to use it for byte cache. Now I have 32. Yeah. So because I have 2 to k way set associative cache, it means that each set has 2 to k blocks in it. So that means that I need 32 minus n plus k bits for cache tag. Now the number of bits I need for each for the tag has increased. Previously in direct map, I only needed 32 minus n. Now I need to add this k to it for my cache tag, and the rest of it will go to cache index. Now let's look at the example we had. So if you do the math that I have presented here, you'll figure out that you still need 5 bits for your byte select. Now the cache index has decreased because the cache tag has increased. So now the cache tag is, instead of I think previously was 5522, now it's 5 4 and 16. Sorry, no, 8 minus 32, whatever that is. So it actually has to increase. So it's 23 bits, something. Okay, so how do I check now? Now, let's say I have 2-bit, two-way set associative. This means that I will have 2 candidates for each set. Sorry, now I will have two blocks per set. So that basically means as if I have divided my cache into 2. So now I have 2 of those tables, the same as direct map. Now the first thing I do, I use the cache index to index into both of the tables. Then I check my cache tag with both of them to see if I can find a match. It could be either here or here. I have now 2 options for each memory because each set has 2 blocks. So I have to check both of them. So I check them. Now, here I've also added the valid bit. So you have to check if that memory, that cache location is valid. Let's say it is valid, and let's say you have found a match here. So you have to just OR them. So it's either here or here. So if any of them has found it, now you have a hit. So at this point, you just use your, so you bring your cache block, the entire block, and you use your byte select to choose which bytes you need, right? So this is your cache block. Now you will use your byte select to see which part of this block you need. And finally, let's look at fully associative cache. In this one, you have as many candidates as the number of blocks in your cache. So basically, you get rid of the cache index anymore. You don't need the cache index. Everything you're going to use basically everything you have as a cache tag. You still have byte select if you have blocks that have multiple bytes. So you basically now have to search all your cache. So at this point, you have to check your tag with all the tags that you have here. So you're searching for a match here. If you find a match and if that bit for that block is valid, then you have a hit. And if you have a hit, you can just use your byte select to find the byte that you need. Now, just before I end this lecture, as you can see, coming from direct map to two-way set associative and now to fully associative, the reason that fully associative is very flexible. Your memory could be anywhere in the cache. You have freedom in where to put your memory block. But this comparison here, comparing your tag with every single tag, requires a lot of hardware and time consumption. So as a result, fully associative caches, although more flexible, they're slower. And direct map caches are much faster because you don't need any of this. You just need to compare the tag for one block. With two-way set associative, we needed to check the tag for 2 blocks. With four-way associative, you need to check tag in 4 blocks. And this is basically extra hardware. Extra hardware means more area. More area means it's slower because you need to distribute your clock rate. Okay. Okay. With that, I'm gonna end this lecture. So thank you to everyone who attended the lectures. Sorry I went beyond the allocated time. Take care, be safe, talk to you on Friday. Bye-bye.